In this video, you'll be looking at the multiple choice questions from Edexcel Chemistry Unit 1 from the year May 2016. So question 1. The mass of magnesium ions in 1 kilogram of seawater is 1.3 grams, and we are expected to represent this information into parts per million. So let's write out what we have. 1.3 grams magnesium ions, and it is dissolved in 1 kilogram of seawater. Now what I will try to do is I will leave the numerator as grams, and then I will try to express the bottom, the denominator, into 1 million grams, so that we have parts per million. So 1.3, I'll write it out again. 1 kilogram of water, let's try to move towards the units of grams. 1 kilogram of water will be 1000 grams of water. And remember, we are trying to make the bottom to be 1 million grams. So how do we do that? We will multiply the bottom by 1000, because 1000 multiplied by 1000 we get 1 million. But if we were to do that to the denominator, we have to do the same to the numerator. So we ended up with 1 million grams at the bottom of water, and the top we have 1.3 multiplied by 1000, grams of magnesium. So this is actually what we are aiming for. We have 1300 parts per million, right? And then if you look at our options here, this is expressed in standard form. Option B is 1300 parts per million. Number 2, calculate the total number of ions in 7.41 grams of calcium hydroxide, and we are given the molar mass and the Avogadro's constant. So let's start off with this information, 7.14 grams of calcium hydroxide. Let's find out the number of moles of calcium hydroxide. We have to use mass, 7.41 over the molar mass, 74.1. So we know that there are 0.1 moles of calcium hydroxide. Now, how many ions are there? I'll try to write it in an equation so that it's clearer. For every 1 calcium hydroxide, 1 unit, we will have 1 calcium ion and 2 hydroxide ions, right? Because it's bracket 2. So if we have 0.1 moles of calcium hydroxide, we will have 0.1 moles of calcium ions and twice the amount of hydroxide ions. So this will give us the total number of ions. In total, we have 0.3 moles of ions. But we have to express it in terms of the Avogadro's constant. We have to find out the total number of ions. So 0.3 moles. Right. This essentially is the Avogadro's number. So 0.3 multiplied by 6.0 times 10 to the power of 23. Right, this is actually the moles. And then if we input in our calculator, we have 1.8 times 10 to the power of 23. That's option C. Question 3. Which of the following has the highest melting temperature? Right, so you do need to have a bit of background knowledge to know what are the types of bonding involved for all these compounds. Right, Mercury is metallic compound, but based on our experiences, we know that mercury is a liquid at room temperature, so it doesn't really have a high temperature, a high melting point. Potassium is also a metal. It is a group 1 metal, and group 1 metals tend to have low melting point. Right, so let's keep that in mind. This is decane, a hydrocarbon. So decanes, these are simple covalent compound. Right, so we don't expect it to have high melting point also. And then we should recognize this silicon dioxide to be the giant molecular structure. Right, where there are strong covalence bonds throughout its structure, so it would require a lot of energy to break the covalent bonds, so it will have the highest melting point. Number 4, which of these has a dative bond? Right, the dative bond is from the hydronium ion. So how does a dative bond form? Let's focus just on water first. Water will have, oxygen will have 2 bonds, one with 1 hydrogen each, and then it will have 2 lone pairs of electrons. And then for H plus ions do not have any electrons, right? It has lost 1 electrons. If you were to visualize, H has 1 electron, and for it to become H plus, it has lost that 1 electron. So what it can do is it will accept a pair of electrons from the oxygen. Right, oxygen will donate 1 whole pair of electrons to H plus. And this is where we will form our dative bond. So D is our answer. Number 5, what is the equation for the first electron affinity? Right, electron affinity basically is the enthalpy change when 1 mole of gaseous atom right, 1 mole of gas atoms accept 1 mole of electron to form 1 mole of ions. Right, if you accept electrons, you will be forming negative ions. So the key thing will be your atoms must be in gaseous state. So if you were to look at the options, sulfur here is in solid state. That's wrong. And then for options B, the sulfur is in gaseous state. It accepts an electrons, right, plus electron, and it forms a negative sulfide ion. So B is our answer. Right, C, the electron is on the other side. Actually, it means that it loses an electron. So sulfur solid here loses electron. And the sulfur gases sulfur here also loses electron. So that's not what we want. Number 6, hydrogen is mixed with oxygen with these volumes, and then we are given the balance equation. We are expected to find the total volume of gas present at the end of the reaction. So what I find to be useful will be we will try to have a table that accounts for the respective volume at the different stages. So we have initial, or the starting, we have the change, meaning whether it increases or decreases, and then we have the final volume. So let's see what information we are given. 100 grams of 100 cubic centimeters of hydrogen is used, and then it is mixed with 25 cubic centimeter of oxygen. There isn't any steam formed at the beginning, so volume of steam is 0. And using a quick observation, a quick comparison, we can see that if we have 25 cubic centimeter of oxygen, it will only require 50 cubic centimeter of hydrogen, because the ratio for every 1 volume we need 2 volumes of hydrogen. Right? So if we have 25 oxygen, we will need 50 hydrogen. We need 50, but actually we have 100 added. So it's important to realize that this is in excess. Right? Or we can say that this is the limiting amount. What is so important about limiting amount? Limiting amount basically means that all of it will be used up. So if we have 25 cubic centimeter of oxygen, we will use all 25 cubic centimeter. And then from here we can see we can calculate the amount of hydrogen reacted. So 25 here. For every 25 we will use up 50 cubic centimeter of hydrogen, because like I said, 1 is to 2. And for every 25 cubic centimeter of oxygen used, we will produce twice the amount of steam, because it is 1 is to 2. So producing, increasing, we will have the plus, right? If it's being used up, we will have the minus, we subtract. So once we are sure what the changes are, we can do a tally. Right? Initial is 100, we used up 50, we have 50 hydrogen left over. Oxygen, we have 25, we used up all 25, 0. For steam, we started off with 0, we created 50, so we have 50 at the end. And then we want the total. Right, the total simply means 50 added to 50, we have 100 cubic centimeter of gas at the end. Number 7, sodium nitrate decomposes. Right, and what is the maximum volume of oxygen, given that we started off with half a mole of sodium nitrate? So there is only one information that we can start off with, and that is this information, half a mole of sodium nitrate. So 0.5 here. Right, and we are interested in the oxygen. So let's check the ratio. For every 2 moles of sodium nitrate, we have 1 mole of oxygen. So 0.5, we will produce 0.5 divided by 2, 0.25 moles of oxygen. So what is the volume of this amount of oxygen? The extra information is, for every mole of oxygen or of a gas at room temperature pressure, it occupies 24 dm cube. So volume of the O2, 0.25 multiplied by 24. So this 1/4 mole will occupy 6 dm cube. Right, so we find the number of moles of oxygen based on the ratio, and then we take that and multiply by the molar volume. Number 8. Excess copper oxide is mixed with this volume and concentration of hydrochloric acid, and we have a yield of 5.5 grams of copper chloride. So what is the percentage yield? So first of all, let us start off with this information: hydrochloric acid. Right, the moles of hydrochloric acid will be the concentration multiplied by the volume. So 2.5 multiplied by the volume. Right. Do remember to change the cubic centimeter to decimeter, right? So that's consistent with the concentration. So we multiply concentration and volume. We know that we need, or we have added 0.1 moles of hydrochloric acid in the reaction. So this is, let's indicate here, 0.1 mole. If we have 0.1 mole, let's find out the expected amount. 0.1, 2:1 for the acid and copper chloride. So we will expect 0.05 moles of copper chloride. Right? Let's write it out here. Expected moles of CuCl2 so this is what we expect. And what is the expected mass? If we were expecting 0.05 moles of CuCl2, the expected mass will be 0.05 multiplied by the MR, which is conveniently provided. So we expect 6.72 grams. Right, this is if there were 100% yield. But we didn't get this amount. Not surprisingly, we got something less than the expected amount. This is the amount that we have, 5.5 grams. So to find the percentage yield, we take the actual amount, 5.5, divided by the expected amount. And then we multiply by 100%. We get 81.8%. That will be A. Part B, right, we are supposed to find the ionic equation for this reaction. Now, ionic equation, a convenient way to do it is, if you see solid, liquid or gas, right, S, L or G, we will not be required to do anything to that particular compound. But if you see aqueous, AQ, right, you will split them into their separate ions. So let's go through this. CuO, right, this is solid, so I will not do anything to it. I will just write it out as it is. Hydrochloric acid is in aqueous form, so I will need to split it up. It is 2HCl, so in its ions form there will be H+, 2 of them, and chloride ions, there are also 2 of them, right? AQ. And then we go to the other side of equation. CuCl2, it is in aqueous form, so we need to split up into its ions. Copper ions, the charge is 2+, AQ, and there are 2 chloride ions, AQ. And finally, we reach water. Water is in liquid form, H2O. So we will not do any changes to it. We'll just write it out as it is. And then finally, we will cancel whatever appears the same on both sides of the expression. Right. We have chlorides here and 2 chlorides on the other side. So for the rest of them, they do not appear on both sides of the equation, so they are left alone. So finally, we have our ionic equation that corresponds to option B. Right, only the chloride ions were cancelled out. Part C. Which of the following gives the best evidence that the bonding in copper chloride is ionic? So let's look at the options. It has a melting point of 620. Now, we know that generally ionic compounds have relatively high melting point, but then question is it 620 considered high enough? And also we know that there are certain covalent compounds, giant covalent compounds, that have high melting point also. So having a high melting point is not totally conclusive that it is an ionic compound. It does not conduct electricity as a solid. Now, this is not exclusive to ionic compounds. Alright, covalent compound also doesn't conduct electricity as a solid. So again, inconclusive of it being an ionic substance. It decomposes before it reaches its boiling temperature. Right. Just because it decomposes, again, we cannot conclude that it is ionic. Right. There are covalent substances that decomposes easily also. For example, hydrogen iodide. So ease of decomposition doesn't indicate it is an ionic compound. Right. So that leaves us with option D. Right. In the electron density map, there are no contour lines around more than one nucleus. So what does this mean? Let's look at a diagram below. Right. An electron density map basically is we try to map out the location of the electron at any point in time, and then we might get, in extreme cases, we might get the diagram on the left side where the positive nucleus, right, this is the electron density, the locations of the electrons around it at any time, and then the negative nucleus, the negative ions and its nucleus, the positions of the electrons around its nucleus. So there are no contour lines around more than one nucleus. Basically means that the electron isn't shared across the nucleus. They keep to their own well-defined region. So this is an indication of a full transfer of electrons. There's no sharing. No sharing of electron clouds. So this is a good indication that it is an ionic compound. So contrast that to the one on the right side. Right, we will see that there is some sharing of electrons across more than one nucleus. Right, they are shared between the two nucleus, and if they're sharing across more than one nucleus, is an indication it has semblance of a covalent nature to a certain degree. Right, and since there are no contour lines being shared, no electron clouds being shared across nucleuses or nucleus, then it is an indication that it is ionic. Number 9, we are trying to explain why the melting point of sodium is lower than that of magnesium. So let's look at option A. Sodium atoms are smaller than magnesium atoms. Well, this statement is incorrect on its own, even without seeing whether it's relevant to the melting point. So sodium atoms, we know that it has 11 protons. Magnesium atom have 12 protons. So we will expect the nucleus of magnesium to exert a stronger pulling force to the outer electrons compared to sodium, right? So, and that will cause the sodium atom to be larger in size than your magnesium atom's radius. So statement A saying that sodium atoms are smaller is incorrect. Right? Sodium atoms are larger. B, sodium ions has a larger charge density than magnesium ions. Right? Charge density, if we to express charge density, is the charge on the ion over the size of the ion. Right, so for sodium, it's +1 charge over its radius. And then for magnesium is 2+ charge over its radius. And then we know that sodium ion is actually larger than magnesium. Right, as explained, because due to the larger number of protons that sodium has, or the smaller number of protons that sodium has, and then magnesium will be smaller. So you have a large denominator compared to magnesium, so your overall charge density will be smaller, right, compared to the charge density of magnesium. So statement 2, sodium ions have a larger charge density, is incorrect. Sodium ions has a smaller charge density. Statement C, the repulsion between the ions in sodium is less than magnesium. Right, a quick look at the metallic bonding for sodium. Sodium will be positive ions, right, held together by a sea of delocalized electrons. Whereas for magnesium, the positive ions held by a sea of delocalized electrons. Right, then let's check out the repulsion. The repulsion for sodium is less than magnesium. This is actually correct, right? Because sodium is only +1 charge, it will repel each other with less force than a 2+ repels a 2+. So there is stronger repulsion here. So statement option C is a correct statement, but option C doesn't explain why this has higher melting point. Because if it does have stronger repulsion, it's easier to separate the magnesium ions from each other. It should have a lower melting point, right? Because stronger repulsion, they can push each other away more easily. We can find that we need less energy to separate them. So although there is stronger repulsion in magnesium, it doesn't help explain why magnesium then have a higher melting point. Okay, so statement option C is a true statement, but option C doesn't explain why sodium has a lower melting point than magnesium. D, the number of delocalized electrons per atom is fewer in sodium than magnesium. Right, we will use these diagrams again. For sodium, it forms a +1 charge. So essentially, it donates 1 electron to the sea of delocalized electrons. Whereas for magnesium, it forms 2+ charge. Essentially, it donates 2 electrons per ion to the sea of delocalized electrons. So the sea of delocalized electrons is what's holding the ions together, right? It's what's preventing them from repelling each other away. So the more delocalized electrons you have, the stronger your metallic bonding. So since sodium has fewer delocalized electrons per atom, it has a weaker metallic bonding. Therefore, it has lower melting point. So D is the answer that we are looking for. So it is true that there is stronger repulsion between the magnesium ions, but then having more delocalized electrons more than compensated for it, right, causing it to have an overall higher melting point. Number 10, trends going down group 1. Statement A, first ionization energy of the element. Now, ionization energy is the removal of the electrons from the gaseous atoms for first ionization energy. So let's use lithium and sodium as examples. Right, as we go down the group, the outer electron is located further away from the nucleus. Right, the nucleus with its protons is attracting the electrons. So the further away it is, right, the weaker the attraction will be. So it is easier to remove the electrons as we go down the group. Right, easier to remove electron. Right, since it's easier to remove electrons, as you go down the group, the ionization energy of the element is decreasing. So statement A is correct. Let's look at the other options to see why they are incorrect. Right, lattice energy. Lattice energy is proportional to the charges of the ions, so positive and negative charge, and indirectly proportional to the radius of the ions. Right. And then keeping in mind that lattice energy is an exothermic reaction, so we assign a negative sign to the overall value. So how does this compare down the group? Right, for the charges, because we are talking about just +1 charges and chlorides, it will be consistent down the group. The differences will be affected only by the change in the radius of the ions, of the positive ions. Right? As you go down the group, the size of the ion increases. This means that the numerator here increases, and that means that your overall effect will be, this number will be getting smaller and smaller. Right? But because there's a negative sign attached to it, you'll be less and less negative. Right? Maybe it's confusing to students what is less negative. So maybe let's assign imaginary numbers. Maybe for lithium, right, we found out that just for illustration purpose, these are not actual values. Maybe it was -10. For sodium, right, we know that the numerical value will be smaller. Maybe instead of 10 it was 5, but we attach a negative sign, right? We can see that it becomes less negative. Right? It is not as negative as before. So lattice energy of the chlorides becomes more negative. It is incorrect. Lattice energy, we expect it to be less negative as we go down the group. Right? It is less exothermic. Radius of the atoms decreases. This is slightly easier to explain. Radius of the atoms because we add one more shell, the radius should be increasing. Melting temperature of the elements, right? As discussed in an earlier question, the metallic bonding, the melting point is related to the delocalized electrons. And then indirectly proportional to the size of the ion. Right, because of the number of delocalized electrons per atom remains the same, it's also 1 delocalized electrons per atom down the group. What we use to compare will be the size of the ions. The size of the ions down the group increases. Right, because the denominator is increasing, it means that as you go down the group, the melting point decreases. So option D is wrong, because the melting point should be decreasing down the group. Right? Size of ions increase, that's indirectly proportional to the melting point. Which of the following ions has the largest radius? Right, so all of these ions, once you check the periodic table, all of these ions has the same number of electrons. So they all have 18 electrons. What affects the radius will be the number of protons. Right, so 18 electrons, they have the same electronic configuration. So what it depends on is the number of protons. The more protons you have, the larger your attraction, the smaller will be the radius. Or in other words, or conversely, you have less protons, you have less attraction, right, less nuclear effect to your electrons. That means they'll be further away from the nucleus. You will end up with a larger radius. So we have to see which of these 4 options has the least number of protons. Right, that will be, referring to the periodic table, that will be our sulfur. Number 12, 0.1 moles of potassium hydroxide added to 0.1 moles of nitric acid. We get a transfer of energy, 5,200 joules. So let's calculate the enthalpy change in kilojoules per mole. Now, first of all, we realize that since this is in a ratio 1:1, right, these two are actually in exact quantities. So it is fine, we can use either of these as a basis for the calculation. So we know that 5,200 joules was released, and then 0.1 mole of the reactant was used. Now, if you're wondering what happens if the question says it was 0.2 moles here, just for example, and then we must know that this is in excess, right, and then this is the limiting. We will need to use the limiting amount. We cannot say 5,200 divided by 0.2. We cannot use the excess amount. We must use the limiting reagents amount, right? But in this case, the question sets it such that these are the exact quantities. Both of them can be used as limiting amounts. So we use 0.1 here. And then we must know that this is a neutralization reaction. it is exothermic. Right, acid and alkali reaction, exothermic. So we have to assign a negative sign to the enthalpy change. So once we do that, we will find that it is actually negative 52000 joules per mole. And converting it into kilojoules, right, is negative 52 kilojoules per mole. A chemical compound has this composition. What is its empirical formula? Right, the steps are pretty standard. We will try to find out the simplest ratio of the moles. So this is 62.1%. So we assume, as per usual, that the compound is a 100 gram sample. So, right, we start off with the mass. The mass of the carbon in a 100 gram sample will be 62.1 grams, 10.3, 27.6 respectively. And then we will have to find the moles. We divide by their respective relative atomic masses. 62.1 over 12, 10.3 over 1, 20.6 over 16, right? This being their relative atomic masses. And then we end up with 62.1 divided by 12. Let me refer. Five 0.175, 10.3, 1.725. Right, this is the moles, but it is not a nice whole number ratio. So what we can do is we divide everything throughout by the smallest number. In this case is 1.725. So we take this number and divide by the smallest amount, 1.725 throughout. And then we end up with 3, 5.97, which can be rounded up to 6, and then 1. So our empirical formula is C3H6O. Right, that will be D. What is the systematic name of the following? Right, this is an alkane. So let's number the longest chain of carbon we can have. Right, there are two choices. We could number it from here: 1, 2, 3, 4, 5, 6, 7. If you were to do that, right, we will see that our branches landed on, there's a branch at number 4 and a branch, methyl branch at number 5. Whereas if we were to number it from the other end, 6, 7, our branch is now at number 3 and number 4, right? So we always go for the one that allows us to have smaller numbers. So the longest chain is 7. 7 will be heptane. And then we look at our branches. We have a methyl branch here, a CH3 branch, and another CH3 branch here. So we have 2 methyl branches. We call them dimethyl. And then finally we will assign the locations of the 2 methyl branches. They're at location 3 and 4. So we have 3,4 dimethyl heptane. Which of the following shows geometric isomerisms? So we can do a quick sketch of the 4 options here. Propene 3 carbon, double bond. Now propene cannot have geometrical isomers because if you look at this carbon, it has 2 of the same groups attached to it, right? So there will be no geometric isomers for propene. Butene, or but1ene, right? 1 means that the double bond is located at carbon number 1. Okay, again, if we focus down here, this is a double bond. We focus down here, we see that this carbon contains 2 identical groups of hydrogen. So there will be no geometric isomers for but1ene also. Dichloroethene. So this is ethene. 1,1 means chlorine. One of the chlorine is located at number 1 carbon. The other chlorine is also located at the same number 1 carbon. Right. Again, we can see that this carbon has 2 identical groups. And for that matter, this carbon also has 2 identical groups. So there's no way this will have geometric isomers. Right, so our option is D. Let's look at what D looks like. 1,2-dichloroethene. So 1,2, it means that one of the chlorine is on the first carbon, the other chlorine is on the other carbon. Right, so this will have geometric isomers because the carbons do not have identical groups. Right, for that matter, right, this will be the cis isomer. And then if you to draw it in another manner, where the groups are diagonally opposite, this will be the trans isomer. Number 16, we are given 4 skeletal formula, and 16 part A, we are supposed to find compounds that are isomers of each other. So it will be useful for us to figure out the chemical formula. For first one, we have an alkene with just 1 double bond. So the number of carbons here, we have 1, 2, 3, 4, 5, 6. 6 carbon alkene. Since there's only 1 single bond, right, using the general formula CnH2n for alkene, there should be 12 hydrogen. The next compound we have is a cycloalkane. Right, we can use general formulas, or we can use the idea that each carbon should have 4 bonds. So this carbon, 2 bonds are used to be bonded to carbons. So it has 2 hydrogen. 2 hydrogen. Same for the others. Right, each carbon has 2 hydrogen here. There are a total of 5 carbons and 10 hydrogen for the second compound. The third compound, you should recognize it to be an alkane. 1, 2, 3, 4, 5. 5 carbon alkane. And using the general formula CnH2m plus 2, there are 12 hydrogens for this third compound. Last compound is a cycloalkane. There are 6 carbons here. Right, the hydrogen 2, 4, 6, 8, 10, 12. So these are their respective formulas. Which one are isomers? Isomers, again, same function, same molecular formula, different structural formula. So number 1 and number 4 are isomers. B. Which compound has the same molecular formula and empirical formula? Right, empirical formula means the simplest ratio of their atoms. If you were to go down the group or down the list here, this is his molecular formula. His empirical formula is actually CH2, right? We can simplify to this ratio. So they don't have the same molecular formula and empirical formula. C5H10, it can be further simplified, right? So its molecular formula and empirical aren't the same. C5H12, there's no further way to simplify this ratio. So C is the answer. And if we do check D, we can further simplify C6H12 to CH2. Right, so D, we confirm that is not correct. Question 17. With a monomer of build 1 in, what would its polymer look like? So let's try to form the monomer. Let's draw the build 1 in. Right, since it's build 1 in, the double bond is located at the first carbon. And then the rest of the molecule looks like this. Now, for a polymerization to take place, we must visualize the double bonds, right, to be in the middle, and then whatever else will be above and below the molecule. So this is essentially what we have drawn, but this particular group would have to be shifted down, right, so that there's space for it to form its single bonds to other monomers. So this whole group, C2H5, will be found here. And then once that is okay, the way that they form polymers will be the single bond will break, and then it will reach out and join to a neighboring monomer. So the structure of the polymer that we are looking for will be B.